This session is about domestic electricity, which is in paper 1, and this covers combined and triple science. The mains electricity supply is an alternating current supply. In the United Kingdom, the domestic electricity supply has a frequency of 50 Hz and a potential difference of 230 volts. You need to know these two values. Direct potential difference is when the charges are pushed in one direction, and alternating potential difference is when the charges are pushed in one direction and then the other and then back again. So it changes direction. You need to know how to wire a plug. A mains cable contains 3 wires: the earth wire, the neutral wire and the live wire. The live wire is brown and it alternates from plus 230 volts to minus 230 volts and back again. The neutral wire is blue and is held around 0 volts. The earth wire is yellow-green and is around 0 volts. The live and the neutral wire complete the circuit. The earth wire is a safety wire that's connected to the casing of the device. If there's a fault and the live wire connects to the earth wire, it allows a large current to flow and melts the fuse. You can see the wiring of the plug in the top right hand corner. The blue wire, neutral, goes to the left, and the brown wire, the live wire, goes to the right and connects to the fuse because it's the most dangerous wire. We looked at power as the rate of converting energy. Power is equal to the energy transferred divided by the time taken, or the work done divided by the time taken. But when we look at electrical power, we can use 2 other equations. The first is power equals current times voltage. The second one is power equals current squared times resistance. Power is measured in watts, current is measured in amps, and resistance is measured in ohms. So we can calculate the energy transferred by an electrical circuit. We can use our standard equation for power and rearrange it to get energy transferred equals power times time. Or we can use that the energy transferred is equal to the charge times the potential difference. The energy transferred is again in joules, power is measured in watts, T is always measured in seconds, Q is measured in coulombs, and the potential difference is measured in volts. The national grid is a system of cables and transformers linking the power stations to the customer to supply all our houses with electricity. It starts by generating the electricity in the power station, and then a step-up transformer steps the voltage up to a very high value. Here we have 132,000 volts, but they can also use the value 400,000 volts. This enables it to be transferred across the country, losing very little energy as heat. And then when it gets near houses and factories, it steps down the voltage to make it safe to use in houses. A step-up transformer increases the potential difference from the power station to the transmission cables. Stepping up the voltage steps down or reduces the current, and this means that it can lose less energy along the wires as heat. A step-up transformer has more coils on the secondary coil than on the primary coil. A step-down transformer decreases the potential difference for domestic use. This is used for safety in houses, as a high voltage could damage appliances and cause fires. A step-down transformer has more turns on the primary coil than on the secondary coil. But we must remember the conservation of energy. The energy every second, or power, has to stay the same in each coil on a transformer. So the power in the primary coil must equal the power on the secondary coil. Power is current times voltage. So the potential difference in the primary coil times the current in the primary coil has to equal the potential difference across the secondary coil times the current in the secondary coil. This can be seen in the example at the bottom. On the primary coil there is 100 volts and 10 amps, which gives us 1000 watts, and on the secondary coil there is 400 volts and 2.5 amps, which also gives us 1000 watts.